Right, we are in chapter 8, and we're getting to 8.3, which is called partial fraction decomposition. All right, what in the world does this mean? All right, we're not going to even go through the objectives because they are kind of different here. Let's just go to the substance of this section. All right, so partial fractions. What really means is we're going to split a fraction into two different pieces, sometimes 3, sometimes 4. And if you guys remember in algebra, remember going from the right-hand side to the left-hand side over here. Notice these were called rational equations or rational expressions. What you would have to do is you had to get common denominators here. Once you got common denominators, then you were to add up the tops together here. So what we want to do here, we want to go the exact opposite way. We want to go backwards because in higher mathematics, when we have multiple denominators, we want to split them off into individual fractions here. So we're going to go the opposite way. All right, what's the other thing that we have to think about here is we're going to restrict our discussion here to just in terms of proper fractions. We're not even going to handle the improper case. That's not even what we want to even start doing. That's a little bit beyond the textbook here. So we're going to limit it to proper rational expressions. All right, with that, that means the degree on top has to be less than the highest degree on the bottom. We'll see how that happens there too. All right, the book presents it in terms of cases. There's different cases that we're going to look at, and there's 4 different cases. That's what we're going to see, and then we'll do an application question afterwards. All right, first case is if you look at a denominator, and the denominator is usually it's already in factored form, and they have distinct non-repeated linear factors. So you have x plus 3, x minus 1, just like on the previous slide there. There was a x plus 3, x minus 1 in the denominator. That would be considered the first case. So let's go for it. This is the first case here. Notice the distinct factors x plus 1, x minus 2 right there. So what we do, let me just rewrite it all over again here. We're going to split off these denominators. So there's looks like there was a fraction with a denominator of x plus 1, right? And there was another denominator of x minus 2, because that's how you would get common denominators in the first place. All right, so now the only issue is this right here. We're going to put an a in for the top numerator, and we're going to put a b in for the top numerator of second fraction. And technically what we got to do was we got to find a and b. That's what we do. All right, how do we do this? Well, we do this by multiplying by a common denominator. If we multiply everything by, now let's see, this is kind of the way it works right here. You go like this. You're going to multiply this guy by x plus 1, x minus 2. You're going to multiply this by x plus 1, x minus 2. And this again, x plus 1, x minus 2. When you do that, on the left-hand side, all that cancels. You're just left with 2x minus 7. On the other side, you're canceling x plus 1s, but you still have that x minus 2 that's been multiplied to a. There's a multiplication there. And in this one here, looks like x minus 2 is gone, so we have an x plus 1 that's multiplying the b value. All right, so let's do this here. Let's simplify these guys. Let's distribute the a to the x and also to the minus 2. That leaves us with xa minus 2a. On the other one here, b times x is bx, or xb. b times 1 is b. Now, here's what we notice. We're going to line up certain things here. We're going to line up certain things that are multiples of x, and we're going to line up certain things that are just constant terms. So notice you got these x terms right there. Because you have these x terms, we're going to put those guys together. So let's move them closer to each other. So I got all the terms with x in them over here. All the ones without any terms whatsoever go line up over there. All right, and then what we're going to do, we're going to factor out the x right here. So 2x minus 7, again rewriting the left side here. I'm going to factor out the x, leaves us with a plus b times x. And then this one, I just want to put into a little parenthesis, its own little parenthesis right here. All right, so here's what we got. Notice this is the multiplier to x. Therefore, a plus b has to equal 2 at the end of the day if these guys are equal to each other. Same thing goes here. -7 or -7 is the constant term, right? So this constant term has to then equal that one right there. So this is where we set things up. Okay, so I'm running out of room here, so let me rewrite this real quick here on the next slide. So there's that. Let me do the lines again just to make sure we know. We're going to line up a plus b. A plus b has to equal a 2 if these two terms are going to equal each other, right? And then -7 has to equal a -2a plus b. And as we set these up, we're going to say, look, 2 has to equal a plus b, and the -7 has to equal -2a plus b. But doesn't that look like systems of equations? If we turn it around, let's turn this around here. Let's, instead of 2 equals a plus b, let's go a plus b equals 2. And -2a plus b is equal to -7. This is a systems of equations all over again. Instead of x's and y's, we have a and b's. So you got a choice here. Do this by elimination method or substitution method. That's exactly what we're covered in 8.1. I'm thinking, you know what, for this one, I'm going to just choose the elimination method. I'm going to line up my b values to be opposites here. I'm going to multiply this guy by -1. Therefore, this guy will become an opposite of b. You could have also multiplied the top by 2, and that would have made opposites with the a's. It doesn't matter which one you do first, just like it didn't matter in 8.1 what we did. So no change to the top equation. You could have done it differently. You could have multiplied by 2 on the top equation. That's still fine. But -1 times -2a makes 2a. And -1 times b makes a -b. And -7 times -1 is a 7. And let's add them up. A plus 2a makes 3a. The b's are gone as needed, and that's a 9, so therefore a equals 3. Once we know what a is, let's plug it back in. Let me use the top equation here. A plus b is equal to 2, therefore 3 becomes the a value. And if we subtract 3 from both sides, how about a -1 at the end? All right, what did we just discover? We just discovered that if I'm going to rewrite that fraction as we had, 3 becomes the a value. Look back to the previous slide. 3 should be the number. 3 is the a value. 3 should be the number in front of x plus 1. And 1 should be the value on top of the x minus 2. Now notice we got a -1 for the b value. So what we're going to do is we're going to move that negative. Instead of having a negative on top, we're going to move the negative out in front as a subtraction between the two fractions. All right, the next case. What is the next case? Well, the next case is that we do have to do some kind of factoring first. So notice on the bottom, the one that we had before, they were already in factored form. This one, let's start factoring this down. So I'm thinking I can probably factor out an x right over here. So let's do that first here. Let's factor out an x. The numerator stays the same. We don't want to touch the numerator at all. But this would be x on the outside, and then when we do that, we get ourselves x squared minus 1, and then you realize, oh, hold on, I can still factor this down some more. The x squared minus 1 factors into x plus 1, x minus 1. So let's do that. Again, numerator stays exactly the same, no changes there whatsoever. But now this is x plus 1, and x minus 1. All right, now if you want to go ahead of me and try this yourself, it's going to be a little bit of a long problem here. But see if we can do this. If you want to see the setup as well, we can do the setup together as well. So let's see if you can set up this piece right here. So notice we're going to have 3 different fractions, right? You have a something over x, then you have something over x plus 1, then you're also going to have a something over x minus 1. All right, this is what I got. See if you guys agree with me. I have an a over the x value. I got a b on top of the x plus 1 value, and then I got a c over x minus 1 value. So that's what we're going to try to find right there. All right, now comes the tough part. We're going to use this whole screen just to set up our problem. That's what we're going to do. All right, so here we go. We're going to multiply through, because again, we want to get rid of our denominators, right? We want to see the multipliers to the a, the b, and the c. And so let's do this here. We're going to multiply the top by x, x plus 1, x minus 1. That's going to cancel that, but then this one gets multiplied by x, x plus 1, x minus 1. And by now I think you realize really what you have is you have the multipliers of all the factors besides the one that is, I'm running out of room here, the one that's underneath the a, b, or c values themselves. All right, so for the left side, everything cancels, we're left with just numerator only. On this side, the x's are gone, so we're left with a that's being multiplied with x plus 1, x minus 1. There's the a at the end there. For the next one, a plus 1 is gone, so therefore it's going to be x times x minus 1 times the b value. In this one, x minus 1s are gone, so it's x times x plus 1 multiplied by c. All right, the tough part, here it is. We have to FOIL all this stuff out, expand all this out, and then we want to collect all the x squared terms. And whatever that expression is going to be, it's going to be equal to 3. We're going to collect all the x terms, and then whatever the expression is, we're going to set it equal to 4, and then we're going to collect all the loners, all the constant terms, and we're going to set those equal to 3. Let's go for it here. A lot of multiplication here. So this one we're just going to FOIL. This one you should know already from algebra. X times x is x squared. You got difference of two squares really in a sense what you have here, because the signs are different, but then you have the same exact terms inside there. So let's go for it here. We got ourselves x times x is x squared. The middles are going to cancel, so 1 times negative 1 is negative 1. We're going to multiply that with a. Oh, this one's a little easier here. X times x is x squared. X times a minus 1 is minus x. We're going to multiply that with b. X times x is x squared, and x times 1 is a positive x this time, multiplied by c. And now let's distribute our capital A, our capital B, our capital C, and collect like terms. So how about this? How about x squared A minus A? How about an x squared B minus xb? And then finally, how about an x squared c plus xc? All right, let's at least bunch up the ones that are the same exact exponents. That's what I want to do here first. So all the x squareds sort of together in the same region here. So I got x squared a, x squared b, x squared c. All right, now let's gather together all the x's. In fact, there are 2 right here, yep. Minus xb, and then that little xc all the way at the end. And then our loners. Our loners, hey, we just have a minus a over here, that's it. All right, I think we're ready here. Let's factor out the x squareds, so we see what's the multiplier. So a plus b plus c would be the leftovers after we would factor out x squared out of each one of these numbers here. Right there, right there, right there. As we factor the x out of this one here, put a little plus sign here. It'll be x. And again, it doesn't matter which way you multiply it by, as long as you know what's your multiplier, what's your variable. So x. Notice that a plus b plus c is on the left side of x squared. This is on the right side of x. It's fine. Minus a is over here. So right, what goes together? So it looks like a plus b plus c. That stuff is going to be equal to 3 because there's a connection right there between. Let me get the laser pointer here. Right there. There's a connection right there. And then let's see, negative b plus c. That's the connection that needs to happen to equal to 4. and then 3 is equal to negative a right there. All right, let's see if we can write it as a system. So 3 connects to a plus b plus c. 4 connects to a negative b plus c, and I like to write them underneath each. It's almost like a big column. Column for a, column for b, column for c. And the 3 is equal to a negative a. All right, we don't normally see it like this. I think the way we normally see systems of equations is the constant term is on the right-hand side. So I'm going to flip them over here. A plus b plus c equals c. Negative b plus c is equal to 4. And negative a is equal to 3. All right, then we start solving stuff. So let me just grab this last piece right here. Since I'm running out of space, I'll move this to the other slide right here. All right, what do we have here? What's so good about this fact is we already have a variable that's by itself equal to a constant right there. That really, in a sense, the third equation. The third equation right here, awesome. If negative a is equal to 3, you know that a is equal to negative 3. Got the first number. Okay, that was a good one. But it's not going to help me. If I plug in negative 3 into here, I'm still have a variable of b, variable of c. Okay, let's do elimination method right here. Because I have opposites for my b values. That's cool. And then once I get that, I'll know what a is already, so I think that will work. Let's go for it here. Let's see, I'm going to write them out exactly the way they are right there, because I want the b's to cancel. And they're already set up for it in the first place, so that's cool. Add them up. I got an a down here. The b's are gone. I get a 2c, and I get a 7. All right, how's that helping me? Is because I know what a is. A is just a negative 3. And now I can solve this guy for c. So let's see, adding 3 to both sides gets me 7 plus 3 is 10. Dividing by 2 gets me a 5. Wonderful, I know what c is now. All right, which one should I choose to tell me what b is? You have a choice, either the top equation or the middle equation. One of those is just fine. I'm going to choose the top. I'm going to choose a plus b equals c. So let's plug that guy in. A is negative 3, we know. B is what we're trying to find, and C is a 5 for us. All right, negative 3 plus 5, simplifying the left-hand side gets me an extra 2 there. As I subtract 2 from both sides, how about a 1 for the B value? Cool, think I'm done. Let's rewrite what we had on the previous slide, now putting in what we know for the A value. A value is a 3. You could put it as a negative 3. The book always writes it as a subtraction in front or a negative in front. So I'm going to put a negative 3 over x. That was my first denominator. My second denominator was x plus 1, and that was the b value. So on top would be the 1 for the b value. My last denominator is x minus 1, and that was a c value, so that's 5. There it is. So I have basically went the opposite way of combining rational expressions. All right, just want to show you. That's the mathematical proper way of doing it. I want to show you a different way that we're going to actually do. Sometimes towards the end, we're actually going to mix both of these things up. So that's the mathematical proper way of doing it. You set up systems of equations, and you find out the answer. All right, little tiny bit of a shortcut. So there's another way to do these, and most of the time it's faster. Not always, but most of the time it's faster. Let's do the same exact problem, and let's see if we get the same exact answer. So this is, I call it the sometimes shortcut. You know how when you take a shortcut, sometimes it's actually longer than the road itself. Well, it happens here as well. All right, so let's go back a few slides before we start going. So go back a few slides, and what I want to get from that slide is this guy inside inside that little rectangle right there. So before we started distributing everything out, collecting all those terms together from the previous slide, I'm going to take that one right in the parentheses right there. Oh, I'm sorry, right in the rectangle right there. All right, let me rewrite it. So another way to do this right there, blah, blah, blah. So there's the one from the previous slide right here. Okay, so here's what we want to do. We want to be able to zero out the factors so we only have one variable remaining. So let's see how this works out. Notice that if I say x is equal to 0, let's just say I say x equals 0. Here's what's going to happen. Notice the 0 is going to go right into there. This whole thing is going to become 0. This whole thing is going to become 0. Why? Because 0 times 1 times c, that's just going to become a 0. This guy's going to become a 0, which is that whole entire term will become 0. Okay, that's what we want to focus on. So you want to focus on things that will zero out the other variables of a, b, c. So let's try this here. So if I plug a 0 into x squared, I get a 0 times 3. 4x would be 4 times 0 is 0. So really on this side, on the left-hand side, I just get a 3 here. All right, but over here, if I say 0 plugged into x is 0 minus, or so 0 plus 1 is 1. 0 minus 1 is negative 1. Like that, and then we have ourselves the multiplier of a. All right, the rest of them, I know they're going to become zeros. Is that right? Because it's going to be a 0 times negative 1, because 0 minus 1 is the b value. Then we got the 0 over here, and this would be a positive 1 times c. But notice the terms with the b and the c in it, I can just scratch those out. Those guys are just going to be zeros anyway. So notice what we get for a. Hey, look at that. 3 is equal to negative a, therefore a equals negative 3. Is that what we got earlier? I think I like this shortcut method. Looks pretty good. Okay, let's do another one here. Let's see if we can zero out some other ones here. All right, what's another one that can zero out these? I noticed that two of these terms, I have x minus 1 over here, and I have another x minus 1. So I'm thinking, you know what? If I choose x equals 1, I'm going to be able to zero out the a and the b this time. So let's go for it here. Plug it in. 1 times 1, or 1 squared is 1. 1 times 3 is 3. 1 times 4 is 4. And then you got the loner at the end here, 3. The other side, this is going to be, looks like 1 plus 1 is 2. 1 minus 1 is 0. That's what I'm looking for. Times a, because that's going to disappear on me. That's cool. Next one would be 1. And this would be 1 minus 1 is a 0 again. Times b. And then I have myself 1 times 1 plus 1 is 2 times c. So notice this time what happens. 4 plus 3 is 7 plus 3 is 10. But the a variable and the b variable are gone. And I'm left with 2c. And if I divide both sides by 2, I get c is equal to 5. Voila. How cool. There it is. So if I can zero out other variables, I can solve for the variable that I want quite easily here. Let's do one more. So it looks like I got c, looks like I have c and a. So now I need to figure out, okay, how do I zero out a and b, a and c, so I can have something left with a variable of b inside it? Well, notice the common factors. X plus 1 is also with a factor of a, and x plus 1 is also with a factor with c here. So how about negative 1? That would zero those guys out. Now let me rewrite this real quick here. Okay, so let's go with it here. So I'm going to write x equals negative 1. If I choose negative 1, negative 1 squared is 1. 1 times 3 is 3. Negative 1 times 4 is a minus 4, and we get ourselves a positive 3 at the end. But here's what I'm looking for. I'm looking for zeroing out right here. Negative 1 plus 1 makes a 0. Negative 1 minus 1 is a negative 2, but who cares, because that's going to go away anyways because of the 0. Negative 1 comes in for x, and then negative 1 minus 1 is negative 2 for the b value. And then negative 1 comes in for x, and then negative 1 plus 1 is a 0 for the c value. And I know those guys are going to be zeroed out. All right, let's see what I got. 3 minus 4 is -1. Plus 3 more makes 2. That's gone. -1 times -2 is 2b. And the c term is gone as well. And we get ourselves a b is equal to 1. Okay, is that what I got for my answers previously? Absolutely. So let's rewrite our answer here using this method here. So -3 over x plus x plus 1 was our remainder, and the b value was on top of that, which is 1. And then we get ourselves plus x minus 1 is the last remainder, that was over c, and c for us is 5. So the exact same thing that we got earlier on the previous way. So practice problem number 2 showed you 2 different ways to solve these here. All right, one is setting up as systems of equations. The other one is sort of like the plug-in values or the cancellation technique here. All right, let's go for it here. Let's go to practice problem number 3, but it's also this case number 2. All right, so what is case number 2 all about? Well, it's the fact that you have x minus a, but you have it to some kind of power, maybe the second power, third power. Notice in the previous examples that we always had, you always had a linear factor like x minus 1, and they were always to the 1 power. We've never had a second power in here. So because of that, we're going to have to do some consideration here. All right, what's the consideration? Is that whenever you have something to the second power, you got to put in their linear factor first, and then you put the linear factor to the second power. If you had something to the third power, then you would put in x minus a to the first power, then you got to put x minus a to the second power, then you also have to put x minus a to the third power. You got to, in a sense, put each of the exponents or degree up to that point, from linear all the way to that point. Let's try it. I think seeing an example, I think, will probably be the best to sort of see it. All right, let's go for it here. So what I have here is x plus 5 on top. I have already in factored form, so that's kind of nice. I have x and x minus 1, but that x minus 1 is to the second power right there. So here's the thing. We don't know whether it was just the denominators were just x and x minus 1 to the second power, or we don't know if there was actually 3 different denominators. One was x, the other one had an x minus 1 to the first power, and then we had another fraction that had x minus 1 to the second. We don't know that. So what we do is we set up a over x. That's the easy one. And then what we do is we set up the other ones here. We're going to say b on top of x minus 1. So if there was x minus 1 form, this will be other than 0. If it wasn't here in the first place, then b would have been 0, and we can discard that completely. All right, then we take this x minus 1, raise it the next power up, x minus 1 to the second. And again, if this was to the third power, then we would have had to do another one, plus d over x minus 1 to the third if this was a 3. So we move up to that exponent value. All right, what I notice here is I have now 3 different variables. Okay, let's go with it here. And what should we do? We should multiply through by common denominator, I guess, and let's see how we can line up the a, b, and the c. So multiplying the left-hand side by x minus 1 squared, and multiplying then each of these pieces by the same exact denominator. All right, on the left-hand side, everything cancels. That's great. X plus 5 is all we have here. On the other side, looks like just the x's cancel. So how about a times x minus 1 squared? On this side, looks like one of the x minus 1's will cancel. Still left with the other one, so really it's x times x minus 1 times b. And over here, x minus 1's to the second cancel, so really just x times c. All right, again, you could do it one of two ways, whichever way you want to do it. Let's see, I figured I should show it to you sort of both ways here. So the next slide shows you the first way. The slide after that shows you the second way, just so you can have familiarity with it. And again, it doesn't matter which way you choose here. All right, so the first way, the normal way we normally do this is we FOIL everything out. So x minus 1 times another x minus 1, what that would give me would be an x squared minus 2x plus 1. This one over here, I would multiply the x times x. So x times x is x squared, x times 1 is minus x, multiplying b. And then this one we can leave pretty much the same. All right, distributing the a's gives us x squared a minus 2xa plus a. Distributing the b from the right-hand side gives us x squared b minus xb. And then the xc at the end, combining all the x squareds together, or at least moving them closer to each other. There's my x squared a, x squared b. Then moving all the x linear factors towards each other. And then moving the constant terms, the one that are by themselves, no other constant term there whatsoever. All right, and then putting it into factorable form here. So let's go with a plus b gets factored out of x squared. I'm thinking, let's see, negative 2a. For this one, we're just going to take out the x in each of those terms here. So now we have the x over here, and then we have the a still at the end. All right, so I think now we're ready. But notice on the left-hand side, right over here, there's no x squared. It's not x squared plus x plus 5. There's not even x squared here in the beginning, in the first place. All right, so when we write these down, we're going to set up like this. We're going to say a plus b is equal to 0. Since x squared is missing, there's no x squared. So that means the coefficient in front of x squared was 0 when we're doing these. All right, the next one down, negative 2a minus b plus c is give me the coefficient of x itself. So in this case, it was 1 up here. And then, I like this. I know one of the variables already. There it is. All right, so this is an easy one here. So automatically, I know from the third equation, I know a is equal to 5. Perfect. Next, especially the equation number 1, that's even easier here. Look at that, a plus b equals 0. So if we put these two thoughts together, we're going to say negative 5 plus b equals 0. Therefore, b has to be equal to 5 because they have to be, sorry, negative 5. They have to be opposites to give you a 0. And once I know that, then I can use this middle equation, knowing what a is, also knowing what b is. I can get the c value now. So that's negative 10. That's a 5 plus c equals 1. So that's going to be a negative 5 on the left. Moving it over to the other side, how about c equals 6? There it is. There's my 3 values already. I'm done. Okay, those that want to do the shortcut method-ish, let's do that one as well. If you did it this way, again, don't need to do it both ways. Just do it one way. That's all I need to do. So if you were to set this up without foiling anything out, think to yourself, what would make zeros here? And first thing to try is 0 itself, because if that's the case, on the left is a 5. 0 minus 1 is negative 1. When you square, it just becomes positive 1. And you know that these guys are going to become zeros because there's a factor of 0 here. There's a factor of 0 there. So we know that a equals 5. Done. Next one. What else can we put in? Oh, x minus 1. That's what we can put in. X minus 1. Or sorry, x equals 1 because of the x minus 1 here. Then I'm going to 0 this out right away. So let's go for it here. 1 into the x here. 1 plus 5 is a 6 on the left. 1 minus 1 is 0. Squared becomes a 0. Let's see over here. We get ourselves... ooh, that's going to become a 0 as well, right? Because you got 1 here, but then you got 1 minus 1 over here. So that zeroes out. So really what we have here is a 1 times c. Therefore we know that c equals 6. All right, now what is something else that can we somehow do? You know, we can't plug in something else because those are the two things that give us zeros. That's it. There is no other. Okay, what do we do here is we can plug in whatever we want. We're just going to we can plug in a positive 2, a 3, a 7, a 12, a negative 6, negative 12. Why do we do it? Because when we plug in one value, we will be left with only one variable that we don't know. That's the key here. Since I know what A is, since I know what C is, let me plug in value. In fact, we do want to plug in something that's not going to cause zeros anywhere here. So a negative 1 would work. If you want, you can plug in a positive 2. That would work as well. So a 3 would work. All right, any one of those. So I plugged in a negative 1. Just sort of see negative 1 plus 5 is a 4. Negative 1 minus 1 is negative 2. If you square that, it becomes 4. So how about 4a? A negative 1 here makes, let's see if we can do this here, negative 1. Negative 1 minus 1 is negative 2. Negative 2 times negative 1 is a positive 2. So are we okay with the positive 2b over here? And this would be a minus c. Okay, notice we have all three variables in here, but we know what a and c is. So we can just put in the value for a, we can put the value in for the c, and we can solve for the one that we don't know yet. I'm running out of room, so let me move to the top here. This is going to be a 20 now, plus 2b minus 6. So on the right hand side, putting together the 20 and the minus 6 makes a 14. And subtracting 14 from both sides gets you a negative 10. And we get ourselves a b is equal to negative 5. All right, is that what we found on the previous slide? Yep, I'm just kind of looking at the previous slide here. That's what we found. B was a negative 5, C was a 6, A was a positive 5, so we can finally write our answer. So over the x variable was the A, now it's a 5. For B it was a minus 5, so we're going to put a subtraction symbol. So subtract x minus 1. Now the 5 on top of that. And then C is equal to 6, so this will be x minus 1 to the second power. That's the degree 2 term. And we have a 6 on top of that, and we are done with that case. All right, the third case. What happens if you have a denominator that you can't factor down? It's just stuck. You can't factor that one down any further. Doesn't go down any further because it's a sort of prime factor there. That's what we've got to deal with now. So let's go for it. Practice problem number 4. So looking at this here, that's nice. It is in factor form, but can we factor down x squared plus 2? I don't think so. That is stuck right here. So here we go. Let's see what we do. We're going to rewrite the problem itself here real quick here. On top, denominator stays, numerator stays. It's already in factorable form on the bottom, so that's cool. So now let's start. Let's begin. So one of the terms is x. So I'm going to put a little a on top. Now careful over here. The next term will be x squared plus 2. But notice on the bottom it's a degree 2 denominator. So when we write the stuff on top, remember we said it's going to be only proper fractions we're dealing with, right? So on top, it could be also degree 1 or degree 0, like this one over here. If this is a proper fraction, x for the a over x, that is a degree 1 polynomial, so therefore on top it should be a degree 0 polynomial or a constant term. Here, x squared plus 2, that's a degree 2, so on top it could possibly be that this is a degree 1 polynomial here. How do we express it? We just say bx plus c. So now notice I have the part with the multiplier of the x, and then I also have the constant term at the end. So because this was 2, I had to put in x equals 1 as an exponent and then the constant term. Okay, so that's the setup for those. Notice this is not a linear factor anymore, right? All the previous ones were linear factors. So if you have degree 2 on the bottom, you got to make this a degree 1 polynomial. If this was a degree 1, then it's easy. Put in one single value because this will be a degree 0 value. All right, and it works the same way. So let's go for it. All right, we're going to multiply everything by that big denominator there, x times x squared plus 2 over here, x times x squared plus 2 over there, and x times x squared plus 2 over there. So on the left, everything cancels. I'm left with just the numerator itself, original numerator. On this one here, the x's are gone. So how about x squared plus 2 times a? And on the other one here, this is going to be x squared plus 2 is gone, so therefore it's going to be x multiplying bx plus c. All right, so here's what we're going to do. We're going to mix. Remember the shortcut that we were talking about? We have the shortcut that we talk about, and then we also have the long process that we do. Here's the normal way we actually do it in mathematics here. Let me take this last row that we have here, the last solution set. Let me put it into the next slide here so we have it. Okay, so going on with the slides here. All right, so before we begin, we're going to check to see if we can produce any kind of a shortcut sort of thing. Now, you can't plug in -2, because if you plug in -2, you're going to get -2 squared is positive 4, plus 2 makes 6. But the question is there any kind of 0 you can make? Yeah, remember one of our denominators is just x, right? And if you look over here, yes, this guy, if we plug a 0 in for x, this whole term goes away here at the end. So if that's the case, we're going to combine the shortcut method and the regular method together. That's the normal way we do it. So x equals 0. What happens on the left-hand side? We're just left with -2. If x equals 0 over here, that means 0 squared is 0 plus 2 is 2, so 2a. And then you know that other part right here is going to be a 0, because that's a 0 there. All right, if that's the case, how about a is equal to -1? So we have, what we really have is we have one piece of the puzzle. That's what we want. All right, in fact, here's a little problem. If you were to do the shortcut method here, you get stuck because there's no other way that you can get still a 0 somehow here. It's impossible. So that's why the shortcut method's sort of like, I can't do the shortcut method anymore. That's okay. Let's go on with the regular method. And sometimes this extra little knowledge helps us out tremendously, and sometimes it doesn't help us out that much. So, but it's be good to sort of check out the shortcut and then go on from there. So that's it. I'm stuck beyond in the shortcut method here. Let's go on the regular method. So rewriting here, just so I have the stuff like I had it on top here, and I'm going to distribute the a over here. On this side, I'm going to distribute the x, so it should be x squared b plus xc. All right, combining the x squareds together and the x's together and the constant terms together all by themselves on one side. So how about the x squareds come together? So x squared a plus x squared b. And then putting the x's together, so how about, there's only one, huh? Just xc. And then I got the 2a at the end. All right, factoring out our variables themselves, the x squared gets factored out, leaves us with a plus b. This one really doesn't need any factoring out whatsoever here. If you want to just write it like this, that's fine too, but x times c is fine as well. And there's your constant term. So let's see if we can write out our values here. So a plus b is equal to 3. C is equal to 5. Ooh, that helps out a lot. And 2a is equal to -2. We already know what a is. A is -1. But the giveaway piece right here, and it's going to work exactly like the previous one did work here. So C is equal to 5. If we plug in the -1 in for the a value, so hey, it works out, right? -1 is the a value because we already knew that, but also we can plug in -a into the first equation that we have, so it just kind of lessens the number of variables we got to deal with. And so C is equal to 5, we got that, and then this, adding 1 to both sides, how about gives you a B is equal to 4. And done. Okay, can you rewrite this out? Can you write it as the final answer? I have the answer on the next slide as well, but all yours to do the answer. Alright, so B equals -1, C is 5, B is 4. So here it is. I'll talk about what's on the bottom over there in just a bit here. So -1 goes on top. Notice you could put the negative in front of the fraction, you could put it on top, whatever you like. And then this one. Remember it was bx plus c on top, right? But b is 4, and then c is 5, so it's going to be written as 4x plus 5 on top of this x squared plus 2. Alright, so you can write it like this, or you can write the negative out in front. Again, this is the same exact concept, same exact thing. That's cool. Alright, on the let's see, on the example problem, what they did, the example problem number 4, when they got the answer, they got fractions for the answer. This is what I want to show you right here. And so if you get fractions for your answer, this is not part of this, so let me kind of draw a little line here. That was one problem, that's another. Alright, if you get fractions for your answer, what you do is that little denominator right there, that is going to go to the bottom. I figure I should mention it because on our example problems we don't get that here. So this is a totally different problem. Example number 4 was totally different from practice problem number 4. But when the book did it, these fractions come in. So negatives go out in front, denominators on top go down as multipliers on the bottom, and again the 5 stays on top, the 4 goes down to the bottom. So this is the normal way we like to see it right here. Alright, and the question always comes up, Mr. H, is the top is still okay? Can you actually write it like this as fractions on top of fractions? Yeah, we could have complex fractions here. Normally we wouldn't. And then normally it says simplify. When it says simplify, you want to put it into lowest terms, and those lowest terms would be the one right here that's on the bottom. All right, we're up to case 4. Let's see what we have here. Let's see a denominator that is repeated and that has also irreducible quadratic factors. Oh boy, this is just getting more and more complicated here. So let's see what we do here. All right, case 4. Find the partial fraction decomposition of this. So notice it's x squared plus 1. That does not reduce. It's irreducible. But then also it's not a linear value, not like x squared plus 2 was for us. Now it has this little 2. So guess what? Just like we did before, we got to take the exponent of 1 in one denominator. Then we have to take the exponent of 2 in the next denominator. So writing this out, x squared plus 1. Now we're going to write it as ax plus b, right? Because this is degree 2, therefore on top should be a degree 1. All right, and we're writing over here, now taking it to the second power. And now we're going to write the top as cx plus d. So again, second degree goes down to a first degree. All right, let me rewrite the problem over here. The original problem, so therefore we can actually multiply both sides by stuff. So we see it in front of us here. All right, multiply by the common denominator, which is x squared plus 1 squared over here. The x squared plus 1 being squared over there, and x squared plus 1 being squared over here. So cancel, cancel. Left with x squared plus 3x plus 1. On this side, let's see, one of the x squares will cancel, right? So we're left with ax plus b multiplying one of the x squared plus 1s. All right, on this side, all of it cancels. Just left with cx plus d. There it is. All right, let's FOIL this out, and then the question is, can I do it the shortcut method here? You can't. There is no way to cancel off everything here, so shortcut method does not even apply here. The shortcut method only applies if they're reducible, if they're factorable, and you can get zeros, and they're linear, that you can get zeros out of it. All right, let me rewrite what we had on the previous slide here, because I'm running out of space. And let's FOIL stuff out. So ax plus b is FOILed out with x squared plus 1, if that's the case. How about ax to the third? As you multiply this way, ax times 1 is ax, b times x squared will be bx squared, and then b times 1 is b. So this would be a FOILing out of this area right here. And let's gather together things that we know. So there's only 1x cubed, that's cool. There's only 1x squared, that's even better. Getting the x's together, I see a ax and a cx. So I'll put those together, and then the loners are b and d, or the constant terms. All right, so let's see how sophisticated we are, okay? Rewriting this in factor form here. Let's see, so I got myself ax cubed, bx squared. The only factored form I need right here is a plus c multiplies x, and then we can put these guys in parentheses already to sort of set them up. All right, let's see. I'm going to convert this now to systems of linear equations here. So a, leave all this little space in the middle for the other variables. Since this guy does not have an x to the cubed, I know a has to equal 0. That's cool, got that one. I got b is equal to 1. That's cool. Then I got a plus c is equal to 3. And then b plus d is equal to 1. So there's 2 variables I know already off the bat. So how about a is equal to 0? B is equal to 1. And because I know that, I can finish off the rest quite easily. The third equation now becomes 0 plus c equals 3. So that tells me that c is equal to 3. And the last equation, the fourth equation, I plug in a 1 in for the b value. So that means 1 plus d equals 1. Subtract 1 from both sides and have a d equals 0. Ooh, okay. So we've got some zeros here that are set up. Let's go for it. All right, can you write the answer already? Because I already have all my values. I got the a, b, c, and the d. All right, so if you want to put it in, I'm going to put in all the pieces here, and then I'll show you how we simplify. Okay, so there's my a, there's my b, there's my c, and there's my d. So how do we simplify this out? Just take out all the zeros. So on top, you should just have a numerator of 1 for the first fraction. On the other side, you should have a numerator of 3x only for the second fraction. And we have pretty much did a decomposition of fractions. That's what we did right there. Example 5. I figured we should show this in the textbook here. This is probably how tough it gets, so I wanted to be able to sort of show it to you, as opposed to leave you hanging with maybe you'll see something like this on the homework where it's like, oh man, this is kind of tough there. So again, this is as tough as it gets right here. If you get through this one, you know what you're doing, know what you're talking about, you did great. All right, I'm going to run out of space quite fast here as we do these. All right, so let's go for it here. Let me just rewrite the individual fractions here. So I see x minus 1. I also see an irreducible form, x squared plus 4. I got to get the degree 1 and then also the degree 2 form right here. Now I can start putting stuff in here. So because this is a degree 1, I can just put a on top of the first fraction. This is x squared. So I'm going to put a linear form, bx plus d. I'm sorry, bx plus c. And then the last one here, again, a degree 2. So I'm going to put a dx plus e into this here. All right, all yours. I'm not going to show this for you. I want you guys to try it yourself. Can you multiply through by common denominator to see what you have left? I'm actually just going to give you the answer. I want you guys to try it yourself here. All right, as you multiply through by common denominator, hopefully this is what you have left, is you got the numerator of the initial problem itself. There it is, all given there, plus 13. And I'm going to run out of space. I know this for sure, so I'm going to rewrite underneath here. This should be going horizontally across, but I need the extra space. So hopefully you have the multiplier to a was x squared plus 4 squared. Hopefully your multiplier to the bx plus c value, again that's the canceling off one of the terms. Therefore you're going to have one of the terms still left for x squared plus 4. Then you also have the x minus 1 term as well. And then your multiplier to the dx plus e is the x squared plus 4 cancels completely, right? So then you have only the x minus 1 term left as the multiplier. Okay, this is where we put things together that might help us later on. So remember that x minus 1, that's a linear form. It's reducible, and it can give me a 0 out of here. So I'm going to do the shortcut method for one of them. I want to say, look, x equals 1, because I know the second term and I know the third term. Those are all going to go to 0. So as I plug in 1 into back to the numerator here, 1 to the 4th power is 1 times 2 is 2. 1 to the 3rd power is 1 with a minus in front. 1 squared is 1 plus 13. 1 times negative 2 is a minus 2, and then I got a 13 as the loner on that side. And as I plug in 1 into here, 1 times 1 is 1. 1 plus 4 is 5, and I square that 5 becomes 25a. All right, and then here, notice if I put a 1 in here, 1 minus 1, that would be a 0. So all this becomes 0. And over here, 1 minus 1 is 0. That also becomes 0. So what do I get for a here? Look, so 2 minus 1 is 1. That's going to be 14. 14 minus 2 is 12. 12 plus 13 is 25. So 25 on the left and 25a on the right. So therefore, we know that a is equal to 1. So there's the shortcut method. I was able to only find one value for a. Shoosh. Okay. Let's go for it then. Now let's start foiling everything out. All right, all yours. Again, this is, like I said, this is as tough as it gets here. So this will be quite a while, quite a challenge to put it all together here still. So we're going to FOIL out x squared plus 4 because we're going to square it, and then we're going to multiply by a. This one, ooh, have fun here. We're going to FOIL all this out and keep on FOILing this out for a while. All right, let's go for it here. So if you did FOIL out x squared plus 4, you get x to the 4th plus 8x squared plus 16. And multiplying bx plus c c with x minus 1, you get bx squared minus bx plus cx minus c. You still have to multiply with x squared plus 4. And at the end here, it should be dx squared minus dx plus ex minus e, if you did it all correctly there. Still multiplying out right here. I still got to multiply this stuff out right here. All right, I was getting confused looking at two different slides here, so what I had to do is I had to bring in the previous slide so I don't have to go from slide to slide. Actually, I can look at the screen itself, and so now I can continue going on with this here. So let's go for it here. So distributing the a gives me this right here. Again, try to do the work yourself as well. And let me just check out something just to make sure I got it right. Okay, yeah, okay. So there's that distributed to the a. Now this is the tough part here. You got to defoil this out still. So bx squared times x squared makes a bx to the fourth. Bx squared times a 4 makes a 4bx squared. Negative bx times x squared gives you minus bx cubed. Negative bx times 4 gives you negative 4bx. Cx times x squared gives you a cx to the third, and cx times 4 gets you a 4cx. Whew, lots of stuff here. Negative c times x squared gives you a negative cx squared, and negative c times 4 gets you a minus 4c. Now I'm really stuck here. It should be a capital C. That should be as high as that 4 there. Kind of lazy. And then this little last part here that really is just going to go down. I'm running out of space. I'm going to just rewrite it here so I have it here. And now we're going to collect all the stuff that we know. So starting with x to the fourth, let's move those closer together. So I got, looks like ax to the fourth, bx to the fourth. Those are only two, so if I combine those together, this would be a plus b, x to the fourth. All right, x to the fourth. All right, then we're left with, let's see if I can combine stuff together. Look for x cubes, any x cubes here. I got a negative b, that's just this one here. I got a plus c, and this one you got to be careful because any little mistake you're going to be thrown for a big loop over here. So I think that's all. Those are my x3s. So now let's look for my x squareds here. I think there should be quite a bit of them here. So how about the 8a plus 4b minus c is over here, so minus c, and then the d value right here, so plus d. There's your multipliers for x squared. And again, running out of room again, let's go with any multipliers to the x value. Looking. There's one right there, negative 4bx, so negative 4b. Another one here, 4cx, so plus 4c. Minus d with x, and also that e over here, so plus e. Those are your multipliers to x. And then finally the loner numbers here. What are the loner ones that don't have any variables of x next to them? 16a doesn't. Minus 4c doesn't. And then this little minus e right here at the end. So there it is. There's what I got. Okay, now can you convert this now into a system of equations? All right, and here's what I got as far as systems of equations go. So a plus b equals 2. Leave a lot of space here for the other variables, c, d, and e. The next one would be negative b plus c is equal to negative 1. That's the coefficient to x cubed. So now for x squared, it'll be 8a 4b minus c plus d gets you that 13. Then the coefficients for x is, or the multipliers to x is negative 4b, positive 4c, a minus d, and a plus e, and that should give you a negative 2. And then the loaner here, so 16a minus 4c minus e gets you the 13 value. Alright, so one thing we do know, that a is equal to 1 all the way from the beginning. So let's use that information right over here. Since a is equal to 1, I think let's use a top equation here. So that means instead of a plus b equals 2, how about 1 plus b equals 2? And if that's the case, how about b is equal to 1? We know that. Now because we know b is equal to 1, let's start equation number 2. Equation number 2 says negative b plus c equals negative 1. And how about a negative of 1 plus c is equal to negative 1? Adding those up, now I know that c is equal to 0. So a equals 1 I know from the previous slide. B is equal to 1 now I know. C is equal to 0. Okay, because I know that, there's two different ways to do it here. You can either go for the third equation, or you can go for the bottom equation, whichever one you like, because if you know a and c, you know how to get e. If you do already know a, b, and c, you know how to get d. So it kind of doesn't matter which way you go. I'm going to use the third equation. So third equation, here we go. A is equal to 1 multiplied to 8. B is equal to 1 multiplied to the 4 minus 0, which is the c value, plus d equals 13. And with that here, I got myself 12 plus d is equal to 13. Subtract 12 from both sides gets me d is equal to 1. Then at that point, you really figure out what you want. Is you can either use the fourth equation, or you could use the last equation, whichever one you like. I'm going to use the last equation to get the remaining variable of e here. So 16 times 1 minus 4 times the c value, which is 0, minus e equals 13. So really it's 16 minus e equals 13. Subtract 16 from both sides. Should get you a negative 3, therefore e equals 3. Alright, that is it. That is the tough one from the book here. So now can we rewrite everything, put them in its place? So what I did is I rewrote from the first slide that we started with this year, with the variables there, the a, b, c, d, e. As there, let's rewrite it knowing what we know now. So 1 is a, let's put it in. B value is 1 and c is equal to 0, so really just 1x plus 0, or just x on top. And d and e, from the previous slide, we know that d is 1, e is 3. So how about x plus 3 on top, and then on the bottom is that denominator right there. There it is. That was the tough one. If you got through that, you still know what you're doing great. Alright, we still have 2 problems to go. This one is sort of like it's a clever way to add, and sometimes you may do this in setting up sequences in series as you set these up in calculus. And then the other one is just an application question of a circuit. Alright, let's go for it here. So the question is this: if you were to add up 1 over 4 times 5 plus 1 over 5 times 6, or we would just say like 1 over 20, 1 over 30, 1 over 42, all the way to the product of 3,111 times 3,112. Is there a way that I can get the answer to this? Well, turns out there is. Let's go for it here. So let's think about the whole concept of what's happening here. That's 1 over 4 times 5. if we were to do fraction decomposition on this guy right here, notice what the pattern is. The pattern really is you got a certain number and then you got the next number. So in this case, if k was 4, this would be 4, and b 4 plus 1 is 5. And notice they're all in that same sequence, right? It's the number and then the next number after that, it multiplies to give you that denominator. So let's do this here. Let's do fraction decomposition on that right there. This will be a over x, right, plus b over x plus c. They're both linear factors, right? They're both proper, so therefore I don't need to go beyond that to do that. All right, with that said, let's go for it. So I think I'm going to multiply everything through by the common denominator, which will leave just a 1 on that side. This will just be the multiplier of x plus, or k plus 1. On that side, it would just be a multiplier of k. All right. Let's see, I'm going to do it the old-fashioned way here. So I'm going to distribute it and see what we get here. So a times k, ak, a times 1 is a, and then we have kb, or bk, whatever, it doesn't matter. Let's put those guys together. So really all the values with k in it gives you a plus b, which is a multiplier to k, and then you got the a all by itself as the loner there. But notice on top we don't have an x value here or a k value on top. There's not k plus 1, it's just a 1. So if I'm going to rewrite this, and if you can you write this into systems of linear equations? A plus b equals 0. Next one is a is equal to 1. So I think we got it here. So since a is equal to 1, plug in the 1 into the top equation. The first equation gets you b is equal to negative b. All right, what do we know? We know the fraction decomposition of 1 over k times k plus 1 is 1 over k minus 1 over k plus 1. Okay, are we good there? So that formula in fraction decomposition form is actually a subtraction of that second element. How does this work for us? Well, let's think of this. Let's do the fraction decomposition of each of these and see if we see a little pattern. So here's let me just rewrite the problem itself, and it goes all the way up to this one right here. All right, what's the pattern that we see? So the pattern that we see and when we would do fraction decomposition is it's really 1 over 4 minus 1 over 5. That's the pattern. That's that composed with decomposed fraction there. All right, the next one would be 1/5 minus 1/6, because that's the next fraction in line. Then we have 1/6 minus 1/7, and then we can go on forever. So how does that help us? So the last one would be 3,111 minus 1 over 3,112. Well, notice there's something that's being subtracted and something that's being added, so they're going to actually negate each other. So that negative 1/5 will eventually, if you're adding them, will cancel off with a positive 1/5 there. And the negative 1/6 will cancel off with the positive 1/6, so on and so forth, that everything in the middle will just cancel off even all the way up to that number there. So instead of having a humongous long thing to add together, getting common denominators here, this really, by pattern, really is just 1/4 minus, or the first term minus the last term. Okay, I'm thinking to myself, let's simplify this. That's it. Look at all that. That whole big thing really boils down to just this one little small problem here. And I'm thinking, does 4 go into 3,112? Real quick, let me just check. 4 goes in 31 7 times. That makes 28. Subtract 28 from 31 makes 3. Bring down the 1. Again, same thing happens here. 7 times 4 is 28. Bring down that guy makes a 3. Bring down the 2, and then that's going to be an 8 this time. So 8 times 4 is 32. Perfect. Okay, so that means if I multiply the 4 by 778 on top and bottom, that will give me a common denominator of 3,112. And on top, 778 times 1 is 778. And as I put this together, 778 minus 1 is 777 over 3,112. There it is. I've just added that weird humongous thing on top, and which I couldn't. There's no way. We'll be sitting here for hours to do something like this. We find the fraction decomposition gives us a little pattern. Find out things cancel each other out. Therefore, we're left with a very simple calculation to do right here. So there it is. All right, and the example in the textbook, I want to do that first, and then we'll do our practice problem with it here. So this is a total resistance. This is in a parallel circuit. If you know electronics or are curious in electronics, Google it. Google parallel circuit and see what's happening there. So we have two resistors that are happening. We want to figure out which resistor is doing which part. How much is each part resisting? So we wanted to figure out what's the, sometimes usually in terms of ohms. So what's the ohms resistance for resistance 1? And what is the ohm resistance for resistance 2? All right, and the book doesn't talk about it. I should talk about it here. So the total resistance, this is how we sort of do it here. Total resistance of a circuit is the reciprocal, and then it becomes like this. It's the summation of the two resistors. Notice that this is actually should be T for total. So resistance total is the reciprocal of the first resistance plus the reciprocal of the second resistance. There it is. So what we have to do is we have to, first of all, work with this guy right here. We have to get this guy, and I think we're going to take the reciprocal of this, right? So notice real quick here, this is R, but the way we do resistance in circuits is 1 over RT, and this is technically RT if you think about it right here. Boom. So let's do this. Let's take the reciprocal of R. So this is by the textbook here. Reciprocal of R gives you this. Hey, this is linear. This is the denominator, right? Multiplied. There's 2 linear factors. So let's decompose this into A over X, the first denominator, or the first factor of the denominator. And then we have B. Over here, we don't need BX plus C because this is already a linear factor. Therefore, it's just going to be a degree 0 on top. All right, we multiply through to get rid of all the denominators here. So that goes away, leaving us numerator. This one will just be a multiplier of x plus 5. This will just be a multiplier of x. And that's what we have here. And then they're doing it the quick way here. This is from the textbook. This is just the example. X equals 0, because you know you're going to get a 0 for the b value. Gives you a is equal to 2. And the quick substitution of x equals negative 5, because this guy's going to become a 0. Gives you a b value of 1. And in that case, we can rewrite this as 2 over x and 1 over x plus 5. And what we do here is we want to still make it in terms of a unit fraction. So we're going to take the reciprocal of 2 over x and make it x over 2. So therefore, we put it in the denominator. We didn't have to take the resistance here because this was already a 1. So no need to do that if that's already a 1. So we have it here. So resistance 1, according to the formula, again, this is the formula again, resistance total equals 1 over resistance 1 plus 1 over resistance 2. So in this case, resistor is given x over 2. Whatever the current voltage, really it's slashing it by 2 in a sense. And then we have this one right here. So x plus 5 is the next one. All right, hours. What does ours entail here? So first things first, again, just following the process here, I'm going to take the reciprocal of r, so 1 over r, and then we're going to take the reciprocal of the fraction itself, so 4x plus 7 on top, and how about an x plus 1, x plus 2 on the bottom. And now let's split them off into the two different denominators here. So a over x plus 1. I got a b on top of x plus 2. All right, and let's multiply it out, canceling off common denominators here. Again, you've done this enough times already here. I think you know what happens here. So it's a times x plus 2 with a b times x plus 1. All right, you can do the shortcut method if you like. Go for it. I just kind of did it the long method. This was just me when I was doing it here. But if you did it the shortcut method, go for it. Do it the fast way. I'll do it the long way, and we'll see if we come up with the same answer. All right, the long way would be distributing the a to each of those, distributing the b to each of those, and then collecting all the ones with x's with them, factoring out the x, and then collecting all the constant terms. There they are. So it looks like a plus b would give us the 4, because these guys are connected to each other. The 2a plus b connects to the 7. So in terms of systems of equation here, a plus b equals to 4, 2a plus b equals 7. There it is, and in order for me to cancel one of those, I can either multiply the top by a -2, or I can multiply either the top or bottom by a -1 to cancel off the b values. And that's what I'm going to do. I'm going to multiply the top by -1 for the b values to be opposite each other. So -b there and a -4, just like the way I wanted it. The top no change, the bottom no change. Then at that point here, adding them up, -1 and a +2 makes a by itself. The b's are gone, and we're left with a equals 3. All right, if a is equal to 3, and we know that a plus b equals 4, I know that then the b value has to be equal to 1. All right, so hopefully that's what you guys got the easy way. I did it the hard way here. So what I got here, as in terms of a and the b, I got a 3 for the a value, and I got a 1 for the b value. All right, still that's not the way I want it. I want it all in terms of unit fractions here. So the first fraction here, I'm going to take the reciprocal of it, put it down to the bottom, and then the second one, no need any changes there. So now I got it here. So resistance 1 is x plus 1 over 3. And resistance 2 is going to be x plus 2. All right, so that concludes 8.3 with this new stuff probably you've never seen before in your math stuff.